All right. Good evening, everybody. It's Tuesday. It's Dr. B here, and I see some folks in there already. Loretta, Lindsay, Charlie, Pavel. Welcome, everyone. Say hello if you're there in the chat so I know who's around. Tonight, we're going to look at some molecular geometry, and we've done this bits and pieces before, but it's something that is so essential, not only just to general chemistry, but when you get into that organic chemistry, understanding the shapes of molecules. So that's what we're going to work on tonight. Next week, I won't be here. I'm going to be traveling a little bit, so I won't be around next Tuesday, but we'll pick it up after that. So yeah, let's get started with some molecular geometry. Just to warn you, most of the day I've been doing my taxes and doing my mother's taxes. In the US, we do taxes. They're due April 15th, but they're harder than any chemistry I've ever had to do. So they're kind of a little bit frustrating. So I might be a little bit worn out tonight. So catch me if I make any errors. All right. So yeah, let's do it. Let's try this one here. And we're going to look at it two ways. So you're given a Lewis structure, or sometimes you have to draw it, and you need to figure out the shape of the molecule. So one way is to use a chart like this. And just so you understand, the steric number, that's the number of things attached in the central atom. That's what we always look at the molecular geometry with respect to. So give it a try. See if you can figure out the molecular geometry here. And I was going to try to do a timer. I've never done a timer before. Where's my timer? Here we go. All right, there's a timer. Oh, it did not work. Well, maybe I won't do a timer. Here's my timer, and take 30 seconds since we've already had about 30 seconds for me to figure out how to use the timer. All right. So, Maria, you're saying linear. I see a lot of people saying linear right away. This one might be a little bit easy, but it's a good one to start with. So if we look at this here, the central atoms, the carbon, in all of the electrons here, they're involved in lone pairs. So all of the electrons here on the carbon, they're bonded. So we don't have any lone pairs here. So we have a steric number of 2 because we have 2 things bonded to the carbon, no lone pairs, everything's in bonds. So yeah, it's got to be linear. Here's another way that it ends up being done, though. Sometimes teachers will actually do it this way here. They'll take and want you to use what's called the AXE notation. Does anybody use the AXE notation? So, Charlie, there are no lone pairs on the central atom here, but when they do talk about lone pairs, it is on the central atom. So like we'd have a lone pair on this central atom right here. AXE. So A is the central atom. You have one of those. X, that's the number of things bonded. That's that steric number. So we have 1, 2, and then E would be the number of lone pairs. We don't have any. So typically you just get rid of E. Just delete it. So then what you would do is you'd get a chart and you'd look it up. Hopefully you'd be allowed to have this chart here. And then you would find something that had AX2, and that would be the linear, right? AX2. So those are the two ways you can do it. So some teachers teach one way, some teachers teach the other. It's the exact same way. And you're just trying to think of how things spread out, push each other away, but these are just two ways to do it. I like the chart here, personally. All right, shall we try another one? So this one is an organic compound because we have the carbons and the hydrogens. And when you're given something where you have 2 carbons, you could say this is the central atom and look at the molecular geometry, or this is the central atom. So give that a try. See if you can figure out the molecular geometry. Let's focus on this is our central carbon. Yeah, Loretta, I started out using AXE in my videos, and now I kind of use a mixture because I feel like this is a more visual way to think about it, but some people use the AXE. You know, Charlie, I don't know for AP if they give you the chart. I would probably expect that they wouldn't give it to you, but I can't be definitively telling you that. So, Madhurya, it is a sp3 hybridization. You're correct. So what would our molecular geometry be then? All right. So, Charlie, you're close. So let's look at it. How many things are attached to the central carbon? 1, 2, 3, and then this whole thing here, 4 things. And how many lone pairs are there? These pairs, they're all involved in chemical bonds. So there's 4 things, 0 lone pairs, so it's got to be tetrahedral. If you use the AXE notation to be A, X would have 4 things, no lone pairs, AX4, which is tetrahedral. Right there, tetrahedral. So they give you the same answer. Here's the kind of weird thing about something like this molecule here. When you get into organic chemistry, you have something called Neuman projections. And Neuman projections are kind of interesting. What we're trying to do is, let me make my screen real big here, and then I'll show you. If you take a look at this molecule here, so this is ethane. Because we have a single bond, it can actually rotate on that single bond right there, like this, because it's a single bond. Double bond can't do that. So if you look at it this way, you can see how here everything's lined up. The 2 hydrogens are lined up, but here they're staggered. Because there's like an electron cloud, because there's the valence electrons, this way these are closer, they'll push away. So this is a better, more stable orientation. Even though this is moving, this is the lowest energy. So what we try to draw that, they end up drawing these Neuman projections for you right here, where you can see it's staggered. This is the low energy. In here it's kind of overlapping, called eclipse. This is the higher energy. So if you're taking organic chemistry, you'll be expected to look at these drawings here and discuss which one has higher energy and which one has lower energy. So Neuman projection is kind of an interesting thing in that organic world. All right. How about, I'll move this out of the way so it doesn't confuse us. How about you give this one here a try? What is the molecular geometry? And again, since we have 2 carbons, we just choose one of them since it's symmetrical. Give this one a try. What is your molecular geometry here on this carbon? See if anyone has an idea. This is called ethene. Sometimes you'll see it written like this right here with the double bond. It's our double bond. Trigonal planar. I like that thinking there, Charlie. Because let's look at our number of things. Bent? No, not bent. Let's take a look at it. We have 1, 2, 3 things attached to the central carbon and no lone pairs. So steric number is 3, 0 lone pairs. That's your trigonal planar. And if you did the AXE notation, you'd have A, we have 1, 2, 3, X3, and no lone pairs, so just AX3. If you look that up, that'll be your trigonal planar there again. Let's take a look at that in 3 dimensions. This is kind of an interesting one. So this is a program called MoleView that I really like to use. And you just put the, you can type it in like ethene, and then it brings it up for us. And then we can rotate this in 3 dimensions. So you can see it's flat. And that's that, if you looked at this carbon here, that's your trigonal planar, it's flat. And with this molecule, you can't rotate on a double bond. So this is kind of, these positions are fixed with that. So if we went and looked at a model of it, come over here. If we looked at the model of it here, you can see that it can't rotate on that double bond. It's too rigid. So this is a fixed position. And as a result of that, we have two different ways to describe where the substituents would be on those carbons. So let's go back to this here. And so as you're doing the organic chemistry, watching from India, boards 2024. Uh-oh, that's coming up quick. So if you look at this here, because it can't rotate, you could have 1,2-dichloroethane. Both of these are 1,2-dichloroethane, but this one is called cis because these are on the same side. This is called trans because they're on opposite sides. And that's because this bond right here, this double bond, it can't rotate. It's just too rigid. So as you take organic chemistry, you'll come up with these compounds and you'll have to be able to name them, and you have to think of their molecular geometry to do that. So yeah, let me copy the URL for the app I'm using here. Oh, I just lost it. Where is it? There it is. I'll just copy that and put it in chat for you if you want to try it out now or later. So really helpful when you're trying to study this stuff to visualize in 3D. And also it's really helpful if you're able to get a set of these molecules here, especially when you get to chirality and stereoisomers in organic chemistry. So you can really kind of physically feel what's going on, see how things move and where they're located. These are really worth the money if you can get some of those. All right, so let's go back over and try another one. Here we are. So see if you can figure out the molecular geometry for this one. This one's a little trickier. And so for the benzene molecule here, we have hydrogens. These are all one hydrogen like you're seeing here coming off. And if you look, each carbon does have 4 bonds. 1, 2, 3, 4. So each carbon has its 4 bonds. See if you can figure out the molecular geometry for each one of these carbons. Kind of tricky. So if we think about it, one thing that's kind of confusing is that we have resonance, because really for benzene, these double bonds are all spread out across the molecule. So sometimes you'll just see benzene written like this here. And that's kind of a shorthand. So these are all averaged out. But when we draw Lewis structures, that's a little bit tough to do. So we end up doing this here. But if we just look at this carbon here, let's look at this one right here. It has 1, 2, 3 things and no lone pairs. So steric number is 3, no lone pairs. We get that trigonal planar again. So if they're all trigonal planar, benzene should be flat, shouldn't it? Let's take a look and see if we can see that. Did that answer your question, Fringy? Yeah, Charlie, I like trigonal planar. So we think that if it's trigonal planar, so we're going to go up here and just type in benzene. Benzene. There it is. And if I rotate it, you can see it's flat. And it's because each one of these has that, each carbon has that trigonal planar molecular geometry. Yeah, so kind of fun. All right, let's, so how are we doing? Is this making sense? Is this helping? Any questions you have that we really haven't addressed here? I would say that molecular geometry is one of the things I kind of like. It's such a very visual thing, and it explains a lot of things. Like if you're trying to figure out polarity, you need to understand the molecular geometry. If you're trying to look at how biomolecules interact, or DNA, even interacts or unhinges, and you need to really understand that molecular geometry to do that. This one you get 2 for the price of 1. So what is the molecular geometry here and on this carbon here? So Charlie, so when we draw resonance structures, we end up with the situation like, well, people working on that, I'll show you this here. So say you got ozone, which I think is something like this here. We really can only draw it this way, or we could draw it this way. I'm not drawing the lone pairs right now. And in reality, so you'll see them draw this little arrow here to mean that you have 2 resonance structures. They're not switching back and forth. You have these 2 resonance structures. So in reality, ozone is an average of these 2. So sometimes you'll see it drawn like this here. So instead of a double bond, you have a 1.5 bond here and a 1.5 bond here. And this would be a mix of the 2 resonance structures. I hope that makes sense. So, hey Andy, good to see you there. So if we look at this one, we have 1, 2, 3, 4 things, no lone pairs. 4 with no lone pairs, that's our tetrahedral. So that one is tetrahedral. This one, we have 1, 2, 3 things and no lone pairs, so that's our trigonal planar. So you get really kind of you get used to these main ones that you'll see, and then those are the ones I would commit to memory for an exam, like the trigonal planar, tetrahedral, maybe the trigonal pyramidal, you'll see that sometimes. How is geometry affected by the bond length? I would say there's some effect because your double bonds typically are shorter. I think the big thing is on a single bond, it'll rotate. So you want to think about that. It's not so much the molecular geometry, but the conformations. That rotation is important. But I think at the general chemistry level, you're probably not worrying about taking that into account too much. That would be my take on it. And we can actually go like here. If you look at this here, we could have it like this, and we'd have a tetrahedral molecular geometry. But if one of them was a double bond, it would still be considered tetrahedral. Or if we had 2 double bonds, it would still pretty much be considered a tetrahedral molecular geometry. I hope that kind of answers that, Andy. All right. Let's try another one here. Get a little bit harder here. This is, we have a different part of the table here that has some of the higher steric numbers. See if you can figure out SF. This is SF4. And here we have lone pairs to deal with. Pavel, you asked about like real life examples. Not sure exactly in terms of like why molecular geometry is important, or if you could clarify, I might be able to give you a somewhat intelligible answer. Keeping in mind I've been doing taxes all day, so my brain is a little bit addled. Seesaw is what Charlie's saying. Actually, I have to look at this one, think about it here. So we have 1, 2, 3, 4, and then we count this as well as something that's attached to it. So 5 things with 1 lone pair. Yeah, so it is seesaw. What a great name for a molecular geometry, seesaw. I like that. So when you count the steric number up, you count, really they call them electron domains, because this is like an electron cloud around the fluorine, each fluorine, and then we have our lone pair right there. Let's build this. We have 4 fluorine molecules and 1 lone pair. Let's see what seesaw really looks like. All right, so 1, 2, 3, 4. those are our four fluorine atoms there. And we're going to drop a lone pair in. And lone pairs, they occupy space. They have volume. And there's our seesaw. And you can see it kind of seesawing back. You can imagine a little kid right here, a little kid right here, going back and forth, seesawing. Yeah, so these lone pairs, they really do occupy space. All right. So let's go back over here and give this one a try. SF 1, 2, 3, 4, 5, 6. And FS6 is an interesting one. The Lewis structure here, this was one of the first videos first few videos I did, and you can see I couldn't quite use the program real well. So it was like my F's look all screwed up. But so this is from an earlier video I did, and it's funny to look back at my my skill level. Give that one a try there. So Pavel, you're saying biofuels. So if you imagine, Pavel, like two molecules coming together, and one has something like a trigonal pyramidal molecular geometry where that lone pair is on the top there, and then you have something else that that can almost kind of fit into. If you have a real bulky molecule that's surrounded by, say, tetrahedral alkyl groups like CH3 connected to it, they can get in the way. You call it steric hindrance, and they can prevent the actual bonding. So as you start adding molecular geometries on top of each other, like in more complex molecules, you'll get situations where some molecules will block others, some will be exposed, such that things can fit together, like an enzyme, fitting into a protein and splitting it in half. So that's where it gets real important. They do a lot of that with computers and computational chemistry, but it's the same idea. It's what we're doing right here. So Andy's saying octahedral Charlie is Sparky. Well, let's see. Let's build it SF6 here with no lone pairs. All right. Let me put this app in the chat for you too. This is a free app. It's just on the web. It's really helpful. So we need 6 fluorine atoms. 1, 2, 3. That's our trigonal planar. 4 is our tetrahedral. 5 is trigonal bipyramidal, because you can kind of see the thing in the middle. And our last one is octahedral. Yeah. And we can even put some bond angles in there to see that octahedral molecular geometry. I like octahedral. Yeah, Pavel, certainly you would people working with polymers, they think about molecular geometry all the time. It's almost kind of like in their mind when they're talking, they're visualizing the shapes of the molecules and then how they'll link together, the monomers linking together to form the chains, the polymers. So yeah, certainly. All right. Well, let's try, I don't know how many more of these I actually have. I don't know how many more brain cells I actually have. Here's an aldehyde, because we have the carbon with the hydrogen on the end here. So no chart this time. Just got to figure it out without the chart this time. Make it a little more difficult for you. Don't drink formaldehyde, incidentally, or I guess your heart will explode. Here's what this is looking like to me. All right. So count them up. 1, 2, 3 things, no lone pairs. Not tetrahedral. That would be 4 things like CH4. Steric number is indeed 3. And Andy is saying, and Charlie are both saying trigonal planar. And yeah, I would agree with that. I'm not sure. I think Pavel, when you talk about this being carcinogenic, it's because it's a small molecule as part of it. I think that's a big part of it. And the other part is this carbonyl group here. And it really isn't stabilized by anything on either side because they're just hydrogens. So I think that allows it to attack, for instance, make your heart explode. Although I don't think it would do that. It would probably just give you cancer if you were exposed to it enough. Let's build that. What do we got? We got a double bond with 2 hydrogens. All right, so these would be our 2 hydrogens, and then we have a double bond oxygen. And so you can see it's right in that plane there. It's that trigonal planar. 3 things attached, no lone pairs. Yeah, so I'm confident with that answer. Formaldehyde. And aldehydes have, we'll have your carbon atom here with a double bond oxygen, and then a hydrogen, and the R can be carbons, a bunch of other stuff on it. So this is the simplest aldehyde here with formaldehyde. All right, we're going to end up with electron geometry and the molecular geometry. So we want to figure out both of these. This helps to be able to visualize what this molecule looks like. So Amit, what is bent, the electron or the molecular geometry? Because they will be different. Teachers like to trick you with this one. It's like you're doing the exam, moving through quickly, and you don't catch that it's electron. So okay, I would agree that for water it would be bent. If we went back to our chart, we'd see that we have 4 things, but 2 are lone pairs. So A, X, 2, E2, if we looked that up, it would be bent. If we looked at it on our chart with the steric numbers, it would be bent. But what about the electron geometry? Just think about how they spread out. So we're treating the electrons like atoms almost in that case. So Amit, you're close. So molecular geometry we said is bent. We're good with that. Let's look at it. Let's build the water molecule. So this tool is available to you as you're learning. I recommend you use it every once in a while. And Charlie asks the question of the moment is, yeah, what's the difference? So let's do molecular geometry here. So we said 2 of these here, and we put our lone pairs. And you can see the lone pairs, they push everything down. And water is actually a little different than this. It's 104.5, but they push everything down. If I hid the lone pairs here, you can see why we say it's a bent molecular geometry. The lone pairs, they push everything down, but the molecule's bent. But if you show the lone pairs, we say this is tetrahedral. Tiger prowl tactical. Very nice. Yeah. So it's tetrahedral, and you can kind of see how it's tetrahedral. It has like a tetrahedron, right? So the molecular geometry is when we take into account the electron lone, the lone pairs here for our geometry. So that comes up sometimes. It's kind of a good thing to know. If we actually, with this, we could go and look at, if we go down here, we could look at actually real molecules, and this is actually what water would look like with 104.5 is the actual like experimental bond angle there. Nice. All right, where are we at here? I think that's all I have there. Just open sky. Nothing there. I think I'm going to call it good for tonight. I'm a little bleary-eyed again with all my my tax work I've been doing, and I'm not even done. I'm going to have to work on it tomorrow. So I won't be back next week, but in the following Tuesday I should be here. If you haven't had a chance, go over to my community tab on my YouTube channel. I've been posting a quiz question every day there, and then so you answer it, and then it'll show you the answer and explain why. Maybe show you a video if you need to use it. So a quick way to kind of update your, get a little practice every day. Let me see if I can find it. There it is. That's my channel. So Danny's asking, why do angles change when there are free pairs of electrons? Actually, the reason is, Danny, is these are orbitals. This is an electron cloud. This is all negative. Here it's got a negative, it's got valence electrons. So everything's got negative charges. So it's trying to spread out. And these lone pairs, they're pushing down just as much as the valence electrons here are pushing away. So lone pairs will push those off. Could I do another one of these on equilibrium? Equilibrium, yeah, I keep meaning to do that. Equilibrium's hard. I mean, so I should do one just on equilibrium at some point. So Charlie, I'll put that on my list for that. Yeah, that's a good suggestion. Awesome. So if anybody has any more questions, I could do a few more questions, and then I'm gonna go do something. I don't know. All right. Thank you, Loretta. I appreciate that. And Danny, thank you too. And you like equilibrium too, Le Chatelier and so on. I will put that on my list. That's going to be one I have to really prepare for. That was the thing I was worst at in chemistry class. So I had to make sure I'm doing well. Thank you, Pavel, and you too, Amit there. I will see you guys in, well, I guess about 2 weeks or so. As always, I have my channel there, and if you comment on newer videos, I'm always checking those comments. So that's the best way to get to me. Or there's my email, drb@breslin.org. That's on my YouTube page. All right, everybody. Good night. I'll talk to you soon. This is Dr. B, and as always, thanks for watching. Where are we? There we go.